Good evening, students. Welcome to week 7 problem solving session for Nlog Circuits course. So, in this session, we'll be discussing the leftover problems from last week, which were from filters, and then we'll move into the concepts of oscillators and discuss the problems on oscillators. I am D. Sharda Devi, a PMRF fellow from IIT Gandhinagar. So, let's quickly begin the session today. So, starting with the first problem. In this problem, it is asked that which of the following is input stage of active band pass filter. We have already discussed all different kinds of filters last week, and we know how the band pass filter response looks like, as well as what are the different filters by using which we can design the band pass filters, right? So, how does the bandpass filter's characteristic behavior looks like or frequency response looks like? This is gain, this is frequency. For a bandpass filter, it will pass a band of frequencies by limiting all other frequencies. Alright, this is pass band, and these are stop bands. Okay, so from here, if we observe, so at first we need a high pass filtering behavior, and then we have low pass filtering behavior. So what which of the following is input stage of active band pass filter? So we can see that first we would need a high pass filter, then followed by a low pass filter, right? Now moving on to the next problem. In this problem, we are given a circuit. Okay. Now looking at the circuit, we might or might not decide what is the functionality of the circuit, right? So the best idea to confirm the functionality of any given circuitry is through finding out the transfer functions. Okay, so let's find the transfer function for this particular circuit. So here if we see V out is directly connected to our inverting terminal. So here we would have V out. Now considering since nothing has been mentioned, so if nothing is mentioned, we consider ideal op amp. Hence, we would observe a virtual short concept. Through virtual short concept, we will also observe V out over this positive terminal. So here we will have V out. Now, uh, as we can see that through capacitor C1 and C1 has both terminals at V out. So if two terminals across any particular component, be it resistor, capacitor, inductor, or any other component for say, if VA is VB, VA equal to VB, then potential difference, that is VAB, is 0. Now if VAB is 0, that is the potential difference, if it is 0, we know that if potential difference is 0, then there is no current flow in that particular path, right? So Because of this, we will not have any current over here, right? Across C1. I hope you understood. So the thing is, the potential difference across the capacitor C1 is 0, because of which there is no current flow across the capacitor C1. Now, we also know that in an op-amp, ideally there is no input current as well, right? There is no input current. Uh, Hi Jaykumar, I just started this session, so I can go through the first problem. So I'm going through the problems which we left last time, and then we will go into oscillator based problems. So the first question was that which of the following is the input stage of an active band pass filter. So we discussed last time that band pass filter is a filter that passes a certain band of frequencies, and the frequency response for band pass filter looks somewhat like this. Then if we look into from like lower to higher frequency range, and if we see that okay, what is my input stage first, then we can say that we can first do the high pass filtering, then we can go for low pass filtering to obtain this band pass filtering behavior. So that's why we said that input stage of an active band pass filter is high pass filter. Now coming to the second problem. So in second problem, the question was to determine the transfer function for the circuit given below. Okay. So here I was explaining that, okay, let me come from the beginning. So see, here in this particular circuit, we have V out, and this V out is connected to the inverting terminal, right? Screen is not there. Which screen? My shared screen is not visible to you? Okay, so I can see my shared screen. Maybe I'll share it once again. Wait. Is it visible to you now? Okay, it is visible, right? Okay, chalo. So, did you understand the first problem? The first problem was asked just the input stage of bandpass filter. So, from the profile itself, if I divide the profile into two parts, then I can see in first we encounter a high pass filtering kind of behavior, then low pass filtering. So, that's why we said that input stage of an active uh, band pass filter is a high pass filter. Okay. But definitely we have, sorry. No, there is no need for the circuit, but also we have discussed last time that band pass filter we can go by designing low pass filter followed by high pass filter, or high pass filter followed by low pass filter. The only thing that we need to keep in mind is the cutoff frequencies, that how the cutoff frequencies are designed for those particular filters will basically define how our filter profile looks like. But if I see from the frequency domain also, the first cutoff frequency that we encounter is that of high pass filter. So it is simply we can say that we encounter high pass filtering behavior first, followed by low pass filtering behavior to obtain the band pass behavior. So this was the first problem. Coming to the second problem, so this is the second problem where we have to analyze the circuit to understand, to find out the transfer function and explain the circuit usage. Okay. Screen is visible to you, right? And I'm also audible clearly, correct? Okay. So if you have any doubts, rather than writing in comments or in the chat, please unmute yourself and ask. That is easier for you as well as for me. Okay. All right. So in this particular circuit, now we are asked to find the transfer function of this circuit, right? So starting from this output side, we have V out, which is directly connected to the input terminal through feedback. So we have this V out at inverting terminal. Now, since the nothing is mentioned about op amp, we'll consider it as ideal op amp. So if it is an ideal op amp through virtual ground concept or virtual short concept, here also we would observe V out, right? So V out is observed in both positive, like inverting as well as non-inverting terminals, or positive as well as negative terminal of the op amp. Now, since there is a capacitor connected in between these output as well as positive or non-inverting terminal of the op amp, right? But if we see that the potential difference across the capacitor C1 is zero, as both the voltages are equal. So if both the voltages are equal and potential difference is zero, ideally what would happen? We would not see any current flowing through the capacitor, correct? So there won't be any C1. This is clear to us from the circuit. Now, we also know that the op amp does not have any input current, right? So now see, if your C1 does not carry any current, your input terminal does not have any current, then will there be any current in R2 circuit, like R2 resistor? Will it see any current over here? No, right. Ideally, it should not see any current, right? And if we consider of the KCL also, the KCL will also satisfy. That is only possible when R2 does not carry any current. So the key observation over here is R2 R2 will not have any current flow. So this is the key point that we had to consider in this particular circuit. Now once this is done, the circuit is very simple for us to solve. So now we are only left with, see, now if R2 is not carrying any current, then again the potential difference across R2 should be 0. If potential difference across R2 should be 0, then V out would be the potential that will come at C2, right? So the resultant circuit now that we observe is that of R1, C2, and here we have V out. Now, if I have to write, so I will convert this into the Laplace transform. It is easier for us to uh, write the equations, right? So V out is 1 upon C2S by R1 plus 1 by C2S into Vi. So V out by Vi is 1 upon R1 C2S plus 1. So this is the transfer function that we observe for the given circuit. Now here, by looking just at the circuit, what we would say that there are two capacitors, and so most probably the transfer function or the transfer function should be second order, right? Because there are two capacitors. But here, using two capacitors didn't have any role to play. The capacitor C1 didn't have any role to play. And the final transfer function comes out to be a single order transfer function. And if we observe clearly that this is a single pole system, so which type of operation, so what is the operation that we know which has a single pole system? Yes, it is a low pass filter, right? So this is a low pass filter. So now, see here, this question is a bit tricky because the moment you would see a circuit, it has two capacitors. First thing that comes to your mind is we should always get a second order system because there are two capacitors. But in this question, the one capacitor, that is C1, it didn't have any purpose to it. So what happened is it is just making your circuit bulkier. So it occupies more space on your board, be it a PCB board or an IC design. But at the end, the functionality that the circuit is performing is that of a single order or first order low pass filter, right? So actually, this type of circuit you would observe, but there would be slight change in it, and that we call Salenki topology. It is used for higher order low pass filter circuits and all, but there is a slight error in the placement of components because of which we see this behavior. Okay, so yeah, so this is something which is very important to keep in mind. So that's why it is always safe to calculate the transfer function first, because once you find the transfer function, you have a clarity, and it is 100, you can 100% with surety say that what is the functionality of the circuit, what are the poles, where are the position of poles, zeros, all the information you will have in hand. Okay, so that is the idea. Now, moving on to the next problem. So, in this particular problem, it says that R1 is 10 kilo ohm resistor, and using this 10 kilo ohm resistor, design the op-amp RC circuit given below to realize a high-pass filter with a corner frequency. So, corner frequency is again the cutoff frequency. Okay, so corner frequency, cutoff frequency, um 3 dB frequency, all these are terms used for the cutoff frequency only, and a high pass gain of 10, right? So for the given circuit, it is given that gain, or I should say high pass gain, is 10. If there is no unit involved, then it is always volt by volt. Keep that in mind. Otherwise, you would get gains in dBs, right? If there is mu unit, that means volt by volt or current I by I. So it depends on what is the parameter you are working with, right? Then frequency cutoff is at 104 radians per second. Okay. So since it is radians per second, then cutoff frequency is 1 upon RC. This is in radians per second. If frequency is given in hertz, then it is 1 upon 2 pi RC. This is hertz. Okay. Yeah. So cutoff frequency is given, gain is given, R1 is 10K, 10 kilo ohm. Now here if we observe, this is nothing but a simple inverting terminal or inverting amplifier, right, with R and C components. So if I call this R and C combined together as Z, then my Z is R1 plus 1 by CS, right? R1 is 1 by CS. We know that V out by V in is minus R2 by Z. So that is minus R2 by R1 plus 1 upon CS. This is minus R2 CS by 1 plus R1 CS. So here we can clearly observe that since it is a high pass filter, we are also observing the transfer function with one pole and one zero, which is the necessity for a high pass filter, correct? So here Now this is the cutoff frequency, right? So cutoff frequency, for that we will simply observe the pole frequency. So here the pole is at R1C. So that means the cutoff frequency we can find by simply 1 by R1C. And so if it is 1 by R1C, simply we'll substitute 104 radians per second is 1 by 10 kilo ohms into C. See, when it is asked to design any circuit, the objective of that problem is to find the component values. Okay, so the special component or the component values which are necessary for designing that particular circuit. That is very important. So whenever you see design problems, like design any circuitry, the idea is to find all the component values. Okay, so here the components that we don't know are C and R2. So what we are trying to do is find the values for C, the capacitor, and R2 resistor, right? So since we knew the cutoff frequency, so from there we are finding the value of C through the pole. Okay, so C is nothing but 1 upon 10 kilo ohms into 104. So what is the value of C? If somebody could calculate it quickly, what is the value of C that you are getting for this problem? Yes, what is the value of C?
0.01 microfarad.
Sorry?
0.01 microfarad.
101 microfarad?
0.01 microfarad.
0.01 microfarad.
But
There is a lot.
104.
There is a lot of noise from your side. I cannot hear you. Can you type in the chat?
Hello. Madam, it is 24 or 104?
Oh, this is 104. 104. 104. 104.
Okay.
Yeah.
Okay.
104 came from radians per second. Yes. See, if it was 100, then it would have come across 1 micro.
Madam, it is
Yes.
0.96. Madam, it is 0.96 microfarad.
0.9 microfarad, right? Yeah, it would come somewhat across 0.99 microfarad. Correct. Something across 0.9 microfarad. That's correct. So now we have found out the capacitor value. Okay, can you mute yourself? There is a lot of noise. Yes. So we have already found the value of capacitor. It is coming across 0.9 microfarads. Right? Now we are left with another component, that is R2. We have to find the value of R2. What are the things that we know? We have used the cutoff frequency. Now we are left with high pass gain value, right? So high pass gain, it is given that 10 volt by volt. Now we have seen the transfer function. The transfer function was minus R2 by R1 plus 1 by CS. And here, or I should say, minus R2 CS by 1 plus R1 CS. Both are more or less same. Now here, since it is a high pass filter, we know that in high pass filters, higher frequencies are passed. So the frequency at which we will calculate this gain should be infinite frequency. For low pass filter, you would substitute S as 0 to get the DC gain. For high pass filter, you can substitute the frequency as infinity to find the DC gain. Okay, or I should say to find the pass band gain, right? So here we know that it is minus R2CS1 plus R1CS, and since I have to substitute S equal to infinity, so let's take out S from numerator and denominator. So we will be left with this. Now here, when I substitute for S tends to infinity, what would happen? This term will go to 0 and I would be left with minus R2C by R1C, which is more or less minus R2 by R1. Minus R2 by R1, correct? Now it is given that high pass gain, which is also, as I mentioned, that at very high frequencies we are considering the gain. It is 10 volt by volt. Then R2 by R1, because negative resistance does not have any role, so we can neglect the negative sign. It is 10 times. So R2 is actually 10 times of R1. We already knew that R1 was 10 kilo ohms, which brings us to R2 being 100 kilo ohm. So here R2 is 100 kilo ohm. So for the given specifications, if you want to design an amplifier, these are the components that you would need. That is a 10 kilo ohm resistor followed by a 0.9 microfarad capacitor, and then in feedback you would need a 100 kilo ohm resistor to get the cutoff frequency of 104 radians and a high frequency gain of 10 volt by volt. Okay, is this clear? Is this problem clear? Very straightforward, very simple, direct problem, right? Any doubts in this?
No, madam.
Okay. So
No,
let's
madam.
move on to, so these were the problems for filters. Now let us move on to a new concept of oscillators, okay? Now till now, the circuits that we have seen were amplifiers and filters, right? We said that amplifiers are used to provide gain to the system or to the signal, and filters are frequency selector networks. Now, when we talk about oscillators, oscillators are actually, if I talk about the design of oscillator, how oscillator is designed, so oscillator actually consists of an amplifier followed by a frequency selective network. Which is more or less the functionality of an filter, correct? So what are oscillators? First of all, we need to understand that oscillators are circuit where you do not provide any input signal to them. In oscillators, you don't provide signals to them. What they do is they pick up noise. We always have noise in our signals, in our circuits, right? There are like thermal noise and other different kinds of noise that come into picture. So what oscillators do are, so oscillators already have the supply to them. You have to provide supply voltage, that is VDD and ground will always be provided to all the circuits. We are talking about signal that we give to the input, right? So in oscillators, we don't give any input signal. What it does is it picks up that noise which is already present in the circuit. it slowly amplifies the noise, and there is a frequency selective network. So we know that noise has a huge range of frequencies in it, right? There are multiple random frequencies present in a noise, and it is almost uniformly distributed. So a noise has almost all the frequencies possible. So through the frequency selective network, what oscillator does is, first of all, it starts amplifying the noise to attain a certain magnitude, and then from the noise, a particular frequency is picked. So that particular frequency is picked through the frequency selective network, where it resonates with the frequency selective network. So the frequency of the signal is equal to that of the frequency selective network resonance frequency. Now that particular frequency is picked up, and that frequency starts amplifying, and all other frequencies slowly die down. So at the end, once the oscillations are stabilized, at output, what you start observing is a signal that has a certain amplitude which was decided by you, as well as the frequency that was also decided by you through the frequency selective network. Okay, so that is the purpose of an oscillator. So the things that we need to keep in mind is, oscillators don't need input signals. See, signals, again, I'm specifying signal is not power supply. Signal is input signal that you provide. So it is some waveform that you provide into the circuit. We call them signals. Most of the time, these are AC in nature. So AC signals, we call them as signals, right? But they definitely need supply to work, and the noise that comes will come from that supply noise, or from the circuit's internal noise, or the thermal noise. All the noise, there are different kinds of noises that are present in a circuit uh, while uh, while operating that particular circuit. So in oscillators, they pick up that noise and give you a uniform continuous output. Okay, so oscillators give you a uniform continuous output with defined frequency and magnitude, and it is again defined by you. So when we talk about oscillators, so oscillators are of two types, that is harmonic oscillator and relaxation relaxation oscillator, right? So we have two types of oscillators. One are known as harmonic oscillators, and others are known as relaxation oscillators. What do we mean by harmonic oscillators? That is, the output that you would get is a sinusoidal wave. So here you would get sine wave output. Here you, in non-harmonic, or we can say relaxation oscillator, what we get in output is a non-sinusoidal wave output. So what do I mean by non-sinusoidal wave? So it can be a triangular wave, it can be a square wave, it can be a sawtooth wave, or any other different kinds of waveforms that can be formed. The other waveforms that we see, which are continuous in nature, are obtained through relaxation oscillator, whereas harmonic oscillators give us sine wave output. Okay, and if we talk about what are the components used, so in a harmonic oscillator, we can use an RC based circuit, we can use an LC based circuit, we can use an RL based circuit. So all these circuits can be used for designing a harmonic oscillator. Whereas relaxation oscillators, uh, they would use a certain waveform. Mm. So here again, more or less the structures are same. It is similar to that of amplifier. but we will have some waveform shaping circuits. There would be some circuits which would be used to shape your waveform in a certain way. So we will go through this later, maybe in the coming session. So today we will focus mostly on harmonic oscillators. And yeah, so have you seen these oscillators, or have you come across oscillators anywhere? Or do you know where these oscillators are present?
Madam, crystal oscillator. Crystal oscillator.
Yeah, crystal oscillator is a type of oscillator. Yes, crystal oscillator is a type of oscillator. Laptops, everywhere you will have that crystal oscillator. It is again a type of oscillator, and it is so yeah. There are different kinds of, when we talk about oscillators. There are different kinds of oscillators based on how you form the structures. Like it can be a phase shift oscillator, RC phase shift oscillator. It can be a Windbridge oscillator. It can be a Colpett oscillator. It can be Hartree oscillator. It can be a crystal oscillator. So there are different types of oscillators. The names come from the scientists who have invented those oscillators or came up with the idea of those oscillators. But if I talk about oscillators, so where do you see the use of these oscillators? So all your digital circuits that you're working with, most of them are sequential. They need clock. And when we say clock, it is a square pulse with a defined time period, and it is a continuous pulse. So that pulse is generated through an oscillator. Now when I'm saying a square pulse, that definitely means that it is not using an harmonic oscillator, right? It will use a relaxation oscillator. And also, if you have done lab assignments in electrical and electronics, we all use function generators, right? So those function generators we use, and from there we give the signals to our circuits to test the circuits. And those function generators have all kinds of waves, like sine wave, triangular wave, square wave, sawtooth wave. All different kinds of waves you can find in a function generator. So if we talk about what is the heart of a function generator, so the heart of a function generator is always a oscillator. So oscillator only provides us with the signals, and those signals then we can amplify them to increase the amplitude, and time period can be changed by using the variable capacitors and components like that, variable resistor, capacitor, or an inductor. But the heart of a function generator is always an oscillator, right? So we have seen the examples, like oscillators are present in our laptops, phones, as well as in function generators. Now if we talk about oscillators, so see, first thing I said that one thing that we require, so requirements for oscillators is that it has to pick, first of all, it has to pick a particular frequency which depends on frequency selective network, and it needs to amplify that signal, right? And for that amplification, we know that positive feedback, with positive feedback we obtain that unconditional amplification for the signal. So by using positive feedback, we can get a uh, oscillating behavior. So oscillators can be designed using positive feedback. Okay. So oscillators can be designed using positive feedback. This is one thing. But is it that we cannot design oscillators using negative feedback? That is not true. Because what we need to define, so what is the main criteria to obtain oscillations? We call it as Barkhausen criteria. Okay, once that criteria is satisfied, then you would observe the oscillations. All right. So the name of that criteria is Barkhausen criteria. Once this criteria is satisfied, whatever circuit you have will start giving you oscillations, and you would see output in oscillating fashion. So what does this Barkhausen criteria say, tells you about? So let's say you have an amplifier, and definitely you would need a feedback path, right? Feedback path is always required for the stability. So now you have an amplifier with gain A and a feedback path with a factor of gain beta. Then, according to Barkhausen criteria, for sustained oscillations, you need to have A into beta as 1 or greater than 1. Greater than 1, so while starting the oscillations, you need to have A into beta greater than 1. And when you, uh, so this is actually, yeah, let's say A into beta only, it's fine. So A into beta should be greater than 1, and the phase, overall phase of the circuit, that is including the feedback path as well as the amplifier, it should be either 0 degrees, 360 degrees, or 720 degrees, and so on. So basically, in the factors of 360 degrees or 0 degrees. So this is the criteria for sustained oscillations. Now, if both these criteria are met, then your circuit or the oscillator will give you a sustained oscillation with the defined uh, amplitude as well as the uh, time period of your signal. Okay, so that is the idea of sustained oscillations. But to begin the oscillations, you need to have A into beta slightly greater than 1, so that you can get the oscillations, you can get started with the oscillation, then followed by, after that, if you have already seen the oscillations, then you stop. So practically I am talking about, in the practical lab, if you are performing this experiment in lab, then to begin the oscillation you need to keep A into beta slightly larger than 1. After you get the oscillations, what you do is you tune it to bring A into beta equal to 1 at that time. Now the frequency or the wave that you get, it is sustained and it will go continue to a longer time. So whenever there is a oscillator circuit that you see, and if you want to analyze something, you analyze based on these two criterias only. That is, whether A into beta comes out to be 1, or the uh, overall phase of the circuit, does it come out in the factors of 0 or 360 degrees, and so on. So these are the two criteria which are very important and we have to always keep in mind while analyzing oscillators. Okay, so with this information, let us move on to the problem. So this is the first problem on oscillators, or I can say question number 4 for this particular session. So in this, see, it is said, for a stable sustained oscillation in a system with a loop gain as A into beta, what must be the initial and the final location of poles in the S plane? So we already know that in S plane, that is This is j omega, this is sigma, this is explain. As I mentioned, that right hand side poles and zeros make the system unstable. But here, what we need is these right side poles and right hand side poles. Okay. And to sustain the oscillations, the amplification should not increase drastically. So first, what need to happen is, ideally, your signal should be amplified, amplified, amplified until it reaches a certain level. After that, you want to sustain the oscillations. So if you want to increase the uh, signal, output signal, increase it continuously, what you need is a right hand side S pole. Then if you want to sustain that particular oscillation, we need to make our circuit marginally stable. For marginally stable, what we need to do is, our poles need to stay in the imaginary axis of the S plane, right? So here it is asked that for a stable circuit in a system with loop gain of A into beta, what must be the initial and the final location of poles in S plane? So initially the pole should be in the right hand side of S plane, and after that they should come to the imaginary axis of S plane to make the system marginally stable. Right? Is this clear to everyone? So that's why we need a right hand side pole followed by a imaginary axis pole for marginally stable. So earlier the poles, let's say the poles would be somewhere here. Say the poles were somewhere here. Then what you do is you shift those poles and you bring them here. So this is for marginal stability. And this is the unstable region. And here it is stable region. Yeah, so first you make your circuit unstable, then you bring it to marginal stable to sustain the oscillations. Okay. Now moving on to the next problem. So here it is direct. What is Barkhausen criteria for oscillation of a system with loop gain A into beta in terms of magnitude and phase of loop gain? Yes. What was the Barkhausen criteria? Which option is it? Unity 180, infinity 0, unity 0, infinity 180. Which option would you select for Barkhausen criteria? We already discussed this, right?
Unity 0.
Unity 0. Yes. C option. So for Barkhausen criteria, your magnitudes should multiply to 1 or 0 dBs. Unity or 0 dBs. And your phase should come out to be 0 or 360 and followed. Okay. Now let's move on to the next problem. Okay, so which type of feedback is used in oscillator circuits?
Positive feedback.
Positive feedback. Yes. So the feedback that is used in the circuit is positive feedback, or it should follow Barkhausen criteria. Because in coming problems, we would observe that we are using a negative feedback circuit, but there also we will obtain oscillations. So for oscillations, you can directly use a positive feedback, or you can use a negative feedback, but you can adjust it such that your Barkhausen criteria is maintained, so you would get the oscillations. So if it is, in general, it is asked that uh, for designing an oscillator circuit, what are the requirements? So can negative feedback be used for designing an oscillator circuit? The answer is yes, and we will see the circuits. Okay. Otherwise, the moment you have a positive feedback, you can get the oscillations. The only concern is with positive feedback, the control is not that handy. So user control is not optimal in positive feedback. So that's why people thought of for always keep this in mind. Okay, right. So uh, determine the maximum and minimum frequency of oscillations of Windbridge oscillator circuit having a resistor of 10 kilo ohm and a variable capacitor of 5 nano to 500 nanofarad. So one, we came to a term called Windbridge oscillator. And in this problem, and if I talk about this next problem, so in this next problem, you see there is an op amp and followed by these RC circuits, right? So this is also an oscillator. We call this RC phase shift oscillator. So we'll analyze both these circuits and then we'll solve the uh, uh, problem. So this is Windbridge oscillator is again a harmonic oscillator. Okay. This is a harmonic oscillator. Similarly, RC phase shift oscillator is also a harmonic oscillator. So let's start with Windbridge oscillator. How does this look like? So you would have so here, let's say you have a negative feedback amplifier R1. This is also R1. So this is your amplifier, the basic amplifier that we all know, right? Now, here you would have a capacitor, a resistor followed by a capacitor in series. Then we will have a resistor in capacitor in parallel. Okay, and this connects to yes, this connects to the feedback part. Okay, so this is say RC, this is RC, and here we have R1, R1. Okay, so now see, here we have positive feedback. This is Windbridge oscillator. So you have one RC in series, one RC in parallel, and you have a positive feedback through frequency selective circuit. So this is your frequency selective circuit. This is frequency selective circuit, and this is simple amplifier, right? So in the beginning only I mentioned, right? In an oscillator, we would have one amplifier followed by a frequency selective circuit, right? So the first thing is what we need to keep in mind, A beta should be 1 and phase should be 0 degrees or 360 degrees, right? So see, what is the gain over here? If I talk about A that is amplifier gain and this is beta. So A that is amplifier gain is minus R1 by R1. So this is minus 1. So the gain is minus 1. So if the gain is minus 1, Then for the frequency selective network, see this is capacitor. If I want to find the transfer function for my frequency selective network, this side is output for it, V out dash, and this is V in dash, right? Because you are feeding signal from here, the signal will pass through here, it will come in here, and again this will follow, right? So this is V in dash, this is V out dash. We need to find V out dash by V in dash. This is R, C, this is R and C. So what will be V out dash by V in dash? See, if I say that if this is Z1, this is Z2, then it is Z2 by Z1 plus Z2. Yes. Somebody saying something? No, right? Okay. So I'll convert these capacitors into their Laplace transform form. So Z1 is nothing but R plus 1 by Cs. Z2 is R into 1 by Cs by R plus 1 by Cs, since they are in parallel. So this is RCS plus 1 by Cs, and this is R by RCS plus 1, right? So now V out dash by V in dash, which is nothing but beta. This is Z2 R by RCS plus 1 by Z1. Z1 is RCS plus 1 by CS plus Z2 R by RCS plus 1. Also, we can write like this, that would be easier. 1 by Z2 is 1 by R plus 1 by CS 1 by CS. So this is 1 by R plus CS is 1 by Z2. So Z2 would be you can maybe keep it like this. So it's plus 1 plus okay, anyways. So this is R by RCS plus 1 by RCS plus 1 square plus RCS by CS into RCS plus 1. So these two are cancelled. This will be multiplied here. So beta is RCS upon RCS plus 1 whole square plus RCS. RCS plus whole square C square S square plus 2 RCS plus 1 plus RCS. So beta is RCS upon R square C square S square plus 3 RCS plus 1. Okay. So this is the beta that we obtain. So first of all, see, it is an inverting configuration amplifier, because of which we are getting a gain of -1. So this minus, what does it signify? 180-degree phase shift, correct? This minus signifies a 180-degree phase shift. That means the remaining 180-degree phase shift we need to occupy using our frequency selective network. So that means this beta needs to give us a phase shift of required phase shift of 180 degrees. Okay. So what we will do is we will find the phase of beta and equate it with 180 degrees. Then what we will find is the oscillating frequency omega. Okay, this is the value that we need to find to understand the oscillating frequency. Now, depending on the oscillating frequency, what we will do is we will simply uh, use the values of capacitors and resistors based on that oscillating frequency. So, for 180-degree angle, so this is one idea, that is, you can either go by angle of 180 degree and you solve this to get the value, or what we can do is we can find beta and we can equate it with 1, because we already know that A is 1, right? And we want A beta to be 1. So that means the magnitude of beta should also be 1, A into beta. So beta, if we get beta is 1, then whatever is the value of omega, we can substitute it and um, we'll find the oscillating frequency, right? So we can go by either ways. In both the solutions, like by using both the solutions, we'll get the same results only. Okay. So let's go by the angle one first. So angle, if we are writing angle, first of all, for the 0, we will simply go tan inverse. This is RC omega, right? And then if I have to factorize R square C square S square plus 3 RCS plus 1, factors would be, or roots would be, minus B over B square minus 4 square by We want a phase of 180 degrees. 180 degrees is yeah, right. So since we want 180 degrees, so 180 degrees we can directly go by that. If I ask you tan 180 degrees, so how would it look like? That is sine 180 by cos 180, right? And we know that sine 180 is 0. So that means this angle, that is numerator's angle, should come out to be 0. So, like, yeah, so numerator should come out to be 0. So, based on that, I can simply write that omega is RC. This is because I want my numerator to come to, like, numerator is giving you the value for sine, and denominator is giving you the value for cos, right? So numerator you can simply get 0. By equating that, we'll get RC as so omega as 1 upon RC. Or we can go by beta is RC omega by root under R square C square minus omega square plus this value should equate to 1. So yes, now say omega equal to root under plus R square C square omega square equal to what R square C square. So this is x equal to square minus minus plus 1. So x square minus 10x plus 1 is 0. So it says possible to get a feedback? Oh. You want vanity for vanity degree phase shift, if vanity is acting. Answers. This is going wrong somewhere. Where is it going wrong? This is going wrong somewhere. Yes.
Ma'am, filter resistance is twice of R.
Sorry.
Filter R resistance is equal RS and R1. RS is twice of R1 resistance. I think so. Filter resistance. Yes.
R is twice of R1.
Yes.
You're saying R is twice of R1. Okay, if R is twice of R1, then there is some
Op-amp
mistake.
is operated in non-inverting configuration, so we have to write 1 plus R1 by R1. A is not 1.
Then since it is in okay, yes.
It
This
is in
is
non-inverting.
non-inverting, right? That's where गड़बड़ कहाँ हो रहा है? Right, got it. Yes, correct. This is non-inverting this is non-inverting configuration, right? This particular frequency selective networks output will be fed as input to the amplifier. So this particular configuration is non-inverting amplifier. Now, so this is 1 plus R1 by R1. So A is 2. Now, since A is 2 here, phase is 0 degrees. Yes. Now here, if phase is 0, then simply we can go for 0 degree phase. Phase required is 0 degrees. Then if phase required is 0 degrees, so it is easier to solve for 0. We'll simply so yeah, since the phase required is 0, we'll directly find the phase, that is tan inverse RC omega. So beta is 0 or beta is 2. So if that is the case, then so yeah, we can either go for the phase of beta and substituting the phase of beta, finding the phase of this and equating it with 0, or we can either go by beta as 2, magnitude of finding this beta, and we can equate it with 2 and we'll find the values for omega. So in case of Windbridge oscillator, the omega comes out to be 1 by RC, or frequency of oscillation comes out to be 1 by 2 pi RC. Okay, so this is for Windbridge oscillator. Here in Windbridge oscillator, we are using non-inverting amplifier. That's why we are equating it with the phase of 0 degrees. So the question asked is, for the Windbridge oscillator, when the circuit is 10 kilo ohms and capacitance is C1 is 5 NF, and C1 dash is 500 nanofarad, then what would be the frequency values that we need to find out? So see, whenever we are finding the value of oscillations, the oscillations for oscillation, the frequency that we obtain comes from the frequency selective networks components, that is the R and C of frequency selective networks. So here the 10 kilo ohms that is specified is for the R of the Wien bridge, and C values are also corresponding to the Wien bridge oscillators. And here we keep equal R and C values in both the like series as well as parallel combinations. So yeah, since it is 10 kilo ohms and the values are in hertz, so F oscillation would be 1 by 2 pi 10k into 5 nanofarad. Similarly, F oscillation would be 1.2 pi when we substitute these.
I have one doubt regarding assignment 2. Shall I ask now?
Yeah, I'll finish this problem, then we can go for doubts. Okay. So yeah, in this RC phase shift oscillator, we have again a capacitor followed by an op amp followed by an RC path. C, 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 R, R, R. So the oscillator circuit shown in the figure has ideal inverting amplifier. So since it is an inverting amplifier, so if this is inverting amplifier, we know that phase introduced. So this corresponds to a phase of 180 degrees. That means this remaining circuitry will introduce a phase of 180 degrees. Now from here this is V in dash, and from here this is V out dash um, for the feedback path. So that means this is R C R C R. This is V out dash. This is V in dash. C R C R C R. Now here let's say it is VA, VB, this is V out, 1 by CS, 1 by CS, CS. At VA, so VA minus V in dash by 1 by CS, VA minus minus VB by 1 by CS plus VA by R equal to 0. At VB minus VA by 1 by CS VB by R plus VB minus V dash by 1 by CS equal to 0. So by solving these two, we can get the transfer function of that is V out dash by V in dash equal to the transfer function that we will get. And when we solve this for a phase of, this is beta, so when we solve this for a phase of beta 180, the value that we get for this RC phase shift oscillators, omega oscillations, is 1 upon root 6 RC, and F oscillations is 1 upon 2 pi root 6 RC. This is what we get when we solve this these two equations to obtain the value of V out by V in. Okay. So yeah, these were the basic problems on oscillators. So somebody had some doubt, right? We can quickly discuss the doubt. What was the doubt?
Yeah,
What was
yes.
the
The question is from assignment 2, madam.
assignment 2? Do you
Yeah.
remember the question?
Yeah, yes, madam.
Can you tell me the question so I can?
Yeah. Uh, if you permit, I'll share the screen, madam.
Yes, sure. Do you need some permissions?
Yeah, I'll try to share, madam. I don't know.
Try
Yeah,
to
yes,
share.
madam. Yeah.
Okay.
Yeah, my screen is visible, madam.
Yes, yes.
Yeah, this question, madam. Third question in this.
Where is the third question? Can you bring up the third question?
This one, madam.
I guess my screen is freezed.
Uh,
Are you showing third question to me?
yeah, yes, madam.
Can you reduce the magnification?
Yeah, okay, madam. I'll share once. Is it visible, madam? Now?
Yes, yes, it's visible now. Okay, so if the op amp in question 1 is used as voltage follower, okay, as shown in below, if its slew rate is 0.5 volt per nanoseconds, unity gain bandwidth is this much. Find the rise time from 10 degrees to 90 degrees. The output. Voltage follower. Assuming that slew rate per nanoseconds. Nanogradients per second. Rise time. Okay. So what is the doubt in this? Yes, I got the question. What was the doubt in this?
I want to know the solution, madam. How to do that one?
So this is assignment 2, right? You already must have gotten the solutions.
No,
No?
ma'am. I have the doubt here. I'll share the solution also.
Okay, share me the solution.
The screen is visible, madam.
Yes, 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 it is
Yeah,
visible.
if you look at this, in this, so they
Okay.
are written here 10% of output V naught.
Huh.
Then here they wrote output as 50 millivolts into 1 minus e power minus omega t into t of 10%. I don't know in the next step where that 50 millivolts gone. This step, madam. Is my cursor is visible to you, madam?
Yes, 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 yes. Okay, so see, Vi was 5 millivolts. V out is written 50 millivolts into I e to the power minus um, the value, right? So the maximum, okay.
Yeah, VA they are given it as 50 millivolts only. If you see this problem, first one is 50 millivolts. There is no 5 millivolts, madam.
Okay, so Vi was 50 millivolts. How much? Can you show me once again? Vi was how much?
Question, ma'am.
Yeah, yeah, to the question.
See here, ma'am. They are given the VA as 50 millivolts. First one, second one 100 milli, and third one 1 volt.
Okay, so let's analyze first only. So 50 millivolts into UT is the Vi. All right. So,
In
okay.
50 millivolts, 10% is nothing but 5 millivolts, right, madam?
Yes.
Then why they consider for 5 millivolts? They are asking for output. Rise time for the output signal. So I did not understand this step, madam.
So here, see, the thing is, you have to find the rise time,
Hmm.
and what is that rise time considered is the time. Say, okay, so say this
10%
is
to
how.
90%, that I understand, madam.
Yes.
How they wrote this one, I did not understand.
Okay, so this is say 10%. This is the 90%. So this time frame you need to report it as a rise time. That is the idea that you
Hmm.
got it.
Hmm.
Okay, then if it is 10% of V out is 50 millivolts, 1 minus 10 minutes. 1.1. 5 millivolts. Okay, so you did not understand this 0.1 equal to 1 e to the power minus omega t 10%. This is what you
Yeah,
are
yes,
saying.
madam. Yes. From the above step, how we got the second step, point 0.1 equal
Okay,
to 1 minus.
see, Vi is 50 millivolt into UT. Okay, okay, UT ko let's leave it.
Yeah,
So
yeah,
Vi
UOT
ka,
is 1.
yes, so Vi's 10% is 5 millivolt, correct?
Hmm. Okay.
So this should be output at 10%, right? This is also the output at 10%, correct?
Which one, madam?
5 millivolts. When your output reaches 5 millivolts, that is the 10% time frame, right?
Yes, madam.
Correct? So
Yes.
10% of V naught should be how much? 5 millivolt, correct?
Hmm.
Equal to 50 millivolts into 1 minus e to the power minus omega t into t of 10%, right?
Hmm.
Now, if you divide 5 millivolt by 50 millivolt, how much will be left? 0.1.
Yes. Now clear, madam.
This is clear, right?
Yes.
So that's how they proceeded.
Madam, I have one more doubt. If
Okay.
10, we are calculating for output, right, madam? Why we are
Yes.
considering for input as 5 millivolts?
So
Actually,
the
our input
idea,
is 50
see,
millivolts.
yes, the idea this is the signal that you are providing, right? This is input. It goes
Yeah, yeah.
0 to 50 millivolts.
Hmm.
Okay. And what happens is your output will not change as abruptly as you are providing your input, right? It slowly rises. And the maximum value, since it is a voltage follower, the maximum value of output will also be 50 millivolts.
Yeah,
And it
same
will
as
also
input.
start from 0. Yes, same as input, right? So when we say 10% of output, so 10% of the required output has been reached, that means the 10% of the input's value, right? So it is rising slowly. First, it will reach the 10% of input, that is 5 millivolts. Then 20% of input, 30% of input, and likewise, it will reach the 100% of input. That's when it is the steady state.
Madam, we are providing the step input, right, madam?
Yes,
For step input, step means it is changing from 0 to 1 directly, right, madam?
yes, in input.
Yeah. So how we can calculate step? I mean, rise time for fall time for step signal, madam. It is ramp or sinusoidal. We can calculate. For
Yes.
step signal, how to calculate?
No, no.
Because
So the
it
question
suddenly
is,
changes from 0 to 1. Nah?
yes, yes. But the question is, step is input. But
Yes,
what
madam.
you are considering is output. And output may, to obtain that output, your step input will actually translate into somewhat a ramp kind of behavior.
Yeah,
So
I have
that's
one
why
more
it's
doubt,
so
madam. One more doubt. How they written this response, madam? V naught by Va equal to 1 by 1 plus S by omega t. Because
we
it's a
know.
voltage for because it's a voltage follower. V naught by
Yes.
Va equal to 1.
Yes.
Then why they consider this exponential function, madam? Why they are considering this pole?
Okay, so this actually comes from control systems. So while in control systems, so when there is a unit step function,
Hmm.
because it is not like say you have given a step in input, you
Hmm.
will immediately observe a step in output. That is never the case.
Hmm.
That is where you go for the settling time and all these. So you will definitely have some delay. That's why the delay appears. And that delay which appears, so this 1 minus e to the power minus omega t, this equation, it basically translates to the delay in the output corresponding to input. So it comes
This we
from
can
there.
write for exponentially changing signal, right, madam?
But more or less the behavior is almost similar, so that's why they must have translated it. But basically, you understand, right? For an step input, you would never get an immediate step output. That is never possible. It will slowly rise, and that rise will depend whether that rise is parabolic in nature, or is it ramp like, is it step like, is it exponential. So it all depends on the circuit that you are using. So here the behavior that they have considered is that of a simple delay model. So 1 minus e to the power omega t is actually a simple delay model. So it's simple, like basic normal delay. So wherever a
This I
delay,
understand, madam. This V naught by Va equal to 1 by 1 plus S by omega t. We can write if any RC component is present.
yes, yes,
But
yes,
in our voltage follower, we don't have R and C components.
that
So
is
how
true.
can we represent this as 1 plus S by omega t?
So see, you don't have any external RNC, right?
Yes, ma'am.
But inside your op amp, you have parasitic capacitance as well as resistors present, correct?
Hmm.
From there, you will get the delay, correct?
But generally, we'll write the transfer function for the or externally connected components, right?
Yes, yes. But there we are mostly considering a steady state kind of behavior, right? But
Correct
here,
only, madam. But we are considering ideal op amp, right?
yes, yes, we
So if
consider.
we
So,
consider ideal op amp, we have to bother about external connected element, not about internal things.
no, no. So, see, the thing is that if you look at, see, if I am talking about, say, your time frame comes out to be of rise time comes out to be 10 nanoseconds. Okay. Now, if I am talking about, say, 1 minute time frame, in 1 minute time frame, if I talk about a voltage follower, so by looking at the external circuit, it will be like output is directly equal to input, right? If I'm asking you what is the output at 1 minute, it is directly equal to input. But your rise time is 10 nanoseconds. Now, the idea is to understand what is happening between this 0 nanosecond, like 0 to 10 nanoseconds time frame, which is a very small time frame, right? And in this small time frame, you cannot only consider the behavior of external capacitors, external components, because when the time frames are smaller, you need to consider many other things, because in steady state you will see a certain behavior which is a ensemble of
Then
all
I can
the.
consider this as the transfer function of open loop, madam.
No, it's not like, yeah, means you can consider it for the open loop op amp, but it is more like, so this is basically to uh, consider the delay parameter, how to introduce that delay factor. Because whenever we are trying to analyze op amps, we only consider the external connected capacitors, resistors, or whatever components are there. We analyze the transfer functions based on that, and based on that we are talking about the phase shift introduced, how much is it, blah blah, everything. But in a voltage follower, ideally what should happen, your output should be immediately equal to that of input. Will it ever be possible? Thinking of it practically, it is never possible, right? There is always a delay, and that delay comes from the internal capacitors and resistors that are present, right? So that delay, if you want to model it, because that is a delay. So say practically you have found out this is the amount of delay that you are observing in your, um, or you have found out the slew rate and rise time, fall time of your signals from the input and output. When you compare it in an oscillator, or in a like in your oscilloscope, you will find the rise time, fall time for your signals, right? In a voltage follower. So from there, what you do is you try to model it in form of a delay model. So this 1 minus e to the power minus omega t is actually a delay model. This is used to model delays in the systems. So most of the times when we try to model delays, we write it in this format. So this basically is used to identify the delays. So it is simply a delay model that is used. And to justify that delay model, they have come up with this transfer function of 1 upon 1 plus s omega t.
And one more doubt. If you see here differentiation,
Yes.
so which is if I'll integrate this one,
Hmm.
it will be 0. If I'll integrate this e power minus omega t, it will
Yes.
be like minus, I mean, omega t into t into again e power minus omega t by t, right?
Yes. Yes. Yes.
That term is missing here.
Yeah, the exponential term they have removed, considering that e to the power minus omega t into t, that factor is very small. So they have simply neglected it and they've considered like omega t into v. Or you can say like, see, what if you write dv naught by t, what you will get is omega t into vi into e to the power minus omega t into t, right?
Yes.
So it is like, okay. So
If
now,
it is dv naught by dt is maximum, then
yes,
we can write like this because e power minus omega t term maximum value will be 1.
yes, yes,
Like if I represent that in sine and cos, those values, maximum values are 1, then we
yes.
can write. But they are written only dv naught by dt, they are not written maximum.
Yeah, yeah. So it's dv naught by dt. When you'll write, it will
Yeah,
come up
dv naught
with,
by dt max is nothing but slew rate, then it is correct.
yes. But omega t into vi into e to the power minus omega t t. This is how the term will appear, right? So now, can I Okay, so my screen is shared? No, it's
No,
not.
madam. It is my screen only.
Okay, ma'am. Multiple shares are not allowed. Okay.
Then I'll stop, madam.
Nitty it's okay. Is my screen visible? Tell me.
Yeah, visible, madam.
It is visible, right?
Yes.
Yeah. So see, VI is okay. So VI minus VI e to the power minus omega t into t, and this is VI e to the power minus omega t into t. Mm, VI. Okay, so considering that to write it as omega t into Vi, what are the ways that can be considered? If I consider that this particular value is 1, then I can write dV naught by dt as omega t Vi, right? Correct?
Yeah, correct. If it is maximum,
Or else, yeah, which is
dv
at
naught by dt maximum value is that one.
yes, when t is 0. At that time, I can write this as 1.
Hmm.
Or else, when else I can write it? If I can write that e to the power minus omega t is almost equal to Vi 1 minus e to the power minus omega t into t. Then also I can substitute in place of this. I can substitute this, which is actually V. Okay, so this is V naught, no? No, no, no. So this पे नहीं आएगा. So this is only possible to write when you have this e to the power minus omega t into t term as 1.
The maximum value is 1
The
because t is
maximum is 1.
positive number. The maximum of e power minus omega t is 1, madam.
Yes, that is
Because
possible when
hmm,
t is 0.
yeah,
Yes.
if t is greater than 1 also, it is less than 1 only value. 1 by e power
Yes.
something.
Yes. And t cannot be less than 1.
Hmm.
So so maximum you will get when t equal to 0. And at that time, this is reported as slew rate. Because you want to have a constant value for slew rate, right? So it's like you don't want. So here, from the expression, how it appears is your slew rate is time dependent. Correct?
Yeah, I understand that slew rate, madam. I did not understand about that problem.
Yeah, yeah. So here, what is happening is the slew rate is actually time dependent.
Yes,
But what we ideally want is slew rate to be a constant value. So it is easier for us to analyze, right?
yes,
So that might be the reason that for simplicity, they would have considered this to be 1, saying that it is a constant. And then since omega t into Vi becomes constant, so after that, analyzing the slew rate will be easier. So that must be one reason that they have gone for this, to get a constant value of slew rate. Because this is time dependent value, right? We don't want a time dependent value. So what is the easiest possible way to get a constant slew rate? Let the time is 0. The initial slew rate at t equal to 0 is this much. So we are going ahead with this calculation. Getting my point?
yes.
Yeah, because we want a constant slew rate, right? It is a time dependent slew rate. If I ask you the slew rate at 10 picoseconds, if I ask you the slew rate at 20 picoseconds, it's all different. We don't want that. So what is the easiest possible way is to So at t equal to 0, I know the slew rate and it is a constant value. So keeping that as the slew rate throughout, we are trying to analyze the question just for the simplicity. Okay. Because calculating a slew rate at t equal to 0 is easier. That is the only thing. Right? Any other doubts? Okay. If anyone has any other doubts? If no doubts, maybe we can break over here, and we'll have one class on Monday and another class on Tuesday. We'll have simultaneous 2 classes, and in those 2 classes, uh, maybe in next class I'll try to wrap up the concepts as much as possible. But if we are unable to finish the concepts in next class, I'll take Tuesday class also for covering the concepts, or else in Tuesday's class maybe we can have a summary session where we can go through the concepts which we have discussed once again. Okay. So, yeah.
My side, I have one more query, general query.
Yes.
The questions which you are given in the assignment,
Huh.
those questions, theory part is not covered in the lecture videos as well as in problem solving sessions. Then how to students can answer those questions?
Actually, we are not the part of problem designing, so
Hmm.
uh, we actually don't know. But I did observe this concern that, like, oscillators problem was given in last week's problem,
Yes.
but oscillators were explained in this week's lecture. So
Yeah.
that's
That
why I
oscillator.
didn't. Yeah, yeah, and that is the reason I didn't pick the questions on oscillator last week. I only focused on filters so that I can cover oscillators this week.
No, no,
And
no.
I see.
Actually, you are explained about RC phase shift and Wien bridge, right?
Yes, yes.
They are given some other circuits and they are asking whether they are oscillates or not. If they oscillate, what will be the frequency?
Yeah, yeah. So their Barkhausen criteria is the only. You see, Barkhausen criteria is true for all the oscillators. Whether it is positive feedback, negative feedback, whatever feedback is, Barkhausen criteria works. And if it is a positive feedback, we can directly comment it is like oscillating in
Yes,
nature. But
madam. Without explaining the circuits in the lecture or in the problem solving, how students can analyze those circuits?
no, no. So it's more about you know how to find transfer functions, right?
No,
For
general
feedback.
example, they are cascaded to differentiators, practical differentiator circuits, and they are asking whether it oscillates or not. We know that it's a differentiator, but you are given in the oscillator section. Definitely, the people think that it will oscillate. If
Okay.
one RC is there, they may think that the frequency will be 1 by RC. If two are there, 1 by 2, or I mean 1 by 2 RC. They may think like that.
Yeah, yeah. Okay. So yeah, but, I sort of get it, but it's
Almost 7 to 8 questions are based on that one. They are given the circuit, simply they are asking whether it oscillates or not. If oscillates, what will be the frequency?
okay. So yeah, actually we are not part of assignment designing team.
Yeah, from your end, I gave feedback also, but from your end also, you please share the feedback, your feedback.
Okay, so maybe because the team who is designing the assignments is completely different. So
Yes, even the
we are,
solutions given in the solution manual also not proper.
okay, so if you have some issues in the solutions like assignment solutions on, you can directly write to the forum of the of the
Yeah,
course.
every week feedback is there. Na in that I responded, but written mail I did not receive.
I I think in feedback, it is only for online sessions. Like for our sessions that we are conducting,
No,
there
no,
only.
no. Problem solving feedback is different and lecture feedback is different.
Okay, acha, it's there. Yeah. All right. So, didn't see any improvement after the feedback?
No, no, no.
Maybe you can write into the forum also, because forum is
Okay.
shared with the TAs as
See,
well
when
as.
I compare last time assignments in 2024, the
Yeah.
questions are most are related to videos only and problem solving sessions. This
Okay.
time it is quite opposite.
Means I didn't understand.
Whatever the questions in asked in 2024, this
Right.
course,
Huh?
that assignment courses are covered in the lecture as well as in the problem solving sessions.
Okay.
So this times whatever the problems given in the assignment,
Huh.
not discussed in the lecture as well as not discussed in the problem solving session.
Yeah, this is something actually I felt like the set of lectures and questions which are shared with us. There also, what I felt was that, say, in last week's like problems, there were problems on filters as well as oscillators, but oscillators were not covered last week. Oscillators lectures are covered this week. So that's why I picked the problems of oscillation. I didn't discuss it last time. I added more problems on filters, and I discussed oscillators this week because I know that students have come they have gone through the lectures which are on oscillators this week. Now this week there are problems based on multivibrators and all, but multivibrators I don't think it has been explained this week, right? It is explained next week, I guess. So I also faced that concern, and I had this concern while preparing the problems also, because if you don't have the idea, so I have to go through the concepts, and there is a lot that needs to be covered in a new concept. So in this week, since you had idea of oscillators, I didn't have to go that deep. But otherwise, if I would have covered it last time, so explaining filters as well as explaining oscillators and then covering the problems, we would not have left with any time. So this is something that I too observed from last 2 weeks, I would say. This problem has become a
No,
little
madam. Even in the earlier assignments, up to week two, the questions are related to the contents, but after week three, they are quite opposite questions.
okay, okay,
And
yeah,
parallelly, I am doing the other course, microprocessor and microcontrollers. The
yes.
assignment questions they are covering in the lecture videos.
Oh, okay. That should not happen, because we have strict guidelines that we cannot. So if I try to solve the questions that are already present in your assignments, I cannot do that, so I have to.
No, no, we are not asking whatever the questions you are given in the assignment.
Yeah, yeah,
We
but
have to know the procedure, right? How to solve that.
yes, right,
We are not asking solutions to assignment.
that is true, but at least the concept needs to be discussed prior.
Oh, yes,
No,
I am asking
I
about concept.
agree. I agree with that. Maybe you can write in the forum also, because the team that is designing the assignments is a different team. We don't
Be-
have the contacts,
yeah,
unfortunately.
because if we lose marks in assignment, we cannot score in the end exam.
Yeah, yeah. Because there is a huge weightage to assignments also. I agree. I agree with that. And maybe you write this directly into the forum. So you people have been facing this issue for quite a few weeks, then you would have reported it earlier only.
Madam, every time I am filling the feedback, but I am not responding. I did not receive any response. Even in NPTEL coordinator, I mailed that, but no one responded.
No, but okay. So I guess rather than writing it to the in the feedback form, because what happens is, even the feedbacks that you people are sharing for the problem solving session, no. So I'll receive that feedback after completion of course and generation of certificate. Until then, I would not see the feedback. So similar way, I guess the feedback form response will be shared at the very end. So it's better to write on the forum, because the course TAs, who are the actual TAs leading, like designing the assignments and everything, they will be going through the forum, and forum is a live interactive this. So there you will get the responses also. So forum is a better way to approach, I feel, because in feedback form, I don't know about the course, but if you talk about whether I get your feedbacks on live problem solving session that you submit through the form, the answer is no. I don't get the feedback on the weekly basis. I'll get the feedback at the very end when the course has ended, and when my certificate is generated. At that time, I get the feedback. So I don't get to have the feedback on weekly basis. So I guess if that is the scenario similar in the course as well, the like for the course feedback, then your feedbacks won't be evaluated on the timely basis. So for timely evaluation, I would say forum is the best way. And since it is an interactive way, so you would get the responses also. And then if you don't get the responses, because I guess you have the access to the course TAs also, right? You know the TAs on the course, no? No? Do you know the TAs for the course? Not the one,
In
not,
problem solving session, they are sharing the links,
yes.
and this was my first live session which I'm attending. Just
Okay.
I read that videos,
Okay.
but that also not relevant to the course. I mean assignment, not course, assignments.
Okay. Okay.
Today I have holiday, that's why I attended this course. I mean live session.
Acha. Okay, so we have a certain. All right. This week you have gone through the lectures. Week 7. Have you gone through the lectures? What were the topics that were covered in the lectures?
Oscillators, ma'am. RC phase shift and
Oscillators.
Wien bridge. And
Right.
if you see assignment, you see these questions, madam. How can
Huh.
student will answer? Just I'll share my screen.
Okay. And last week, if I ask you in lecture, in week 6, what were the concepts of the, what were the concepts discussed in the lecture?
Is my screen is visible, madam?
Yes, yes, it is
See,
visible.
madam, all questions they are given like this, whether it oscillates or not. Figures they are given and they are asking. Same repeated questions, circuit they are given and they are asking whether it oscillates or not. And if you look this question, which question? Let me, yeah. If you see this sixth question,
Right.
this will be the practical integrator. They are cascaded, right? Sorry,
Yes, yes,
practical differentiate integrator
yes,
only.
yes, yes.
Now, here three integrators are there. If I go with this question, here
Hmm.
also I have three integrators, right, madam?
Okay.
Different resistor values.
Hmm.
If this circuit is oscillating, and
Hmm.
why can't this circuit not oscillating,
No, so who has said that that will not oscillate?
madam?
Who has said that in this question, question number 6, the circuit is not oscillating? Did anyone say that?
Here they are given, madam. Answer C. Accepted answer is does not oscillate.
Oh, oh, so here it is does not oscillate. In next question, it was
But
oscillating.
here it is oscillating.
And what
What
about
will
the
be
solutions? What about the solutions?
solutions also I saw, madam. They are written like this directly. I don't know what they are written, how they are written also. This will be the answers for that question. See here, they are written this. Loop gain something they are written. Minus 2 tan inverse.
Okay, okay. So see, here they are also coming around with the Barkhausen criteria only.
Barkhasan criteria only, madam. If you see
Yes,
this
yes.
question,
Ah,
ninth question,
yes.
and see the solution of ninth question.
Okay, the loop gain is. Huh.
Here also three poles are there, right, madam?
Yes, yes.
In the sixth question, also three poles we have.
Right.
That three poles are at same position because same
Yes.
RC values are there.
Yes, yes.
And in this case also three poles are there, but they are locating at different places.
Yes.
So here they are written phase angle as minus 540,
Yes.
and why not there 540?
No, so that is the thing, right? So if you have a same R values, so there might be a possibility that, let's say I want 180 degree phase shift. Okay,
Hmm.
I have, let's say, 4 RC circuits.
Madam, in the circuit we require total 360 degrees,
Yes.
and here
So,
it is 540 and 820.
okay.
And in the there they wrote that here the circuit will have minus 720 degrees phase difference
uh,
at some frequency between omega to 0,
yes.
and they are saying it oscillates.
Okay, so it is not like, so see, the question is,
What student will see? They will see either phase shift is 0 or 360,
okay, yeah, yeah,
and
I
they are calculating at omega equal to 0 and omega equal to infinity. Then they are subtracting. If the difference is 360 or multiples of 360, they are saying oscillating.
yes, 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 yes. See, so the thing is, you have a huge frequency range, right? When we were discussing, oh, you didn't attend the stability lecture, no? That is where I
And
said,
here I don't know R2 value and C value. How can I know it will provide that much angle, madam?
no, no, no. See, so here what is happening is, at omega equal to, or yeah, at omega equal to 0 or s equal to 0, whatever you take, j
Yes.
omega equal to
Tan
0.
inverse 0 is 0, right, madam?
Yes, yes, you are
So
getting,
minus 3 into tan inverse 0, it is 0 degrees.
yes,
At omega equal to infinite, tan inverse infinity
yes.
is 90, so minus 270.
So see, let's say I have this in, this is my phase, and say this is, okay. So this is my phase. Here I am getting 540 degrees for.
Can't share your screen. I am not seeing
Oh,
your
my
screen.
screen is not shared. Wait, I'll share it. So generally, what people or what anybody has in mind is, if we are getting the phases in 0 and 360s factors, we will see an oscillation. That is correct. But the question is, are we observing the whole range of frequencies or not? Now, here what happened, for j omega equal to 0, the phase was given as 540. For j omega equal to infinity, the phase comes out to be minus 810.
My question is how they got 540 and 810.
This is by substituting. You have already found the transfer function. You can find the phase of the
Minus 3 tan inverse of some constant, right? But if I substitute omega 0,
minus 3 tan inverse of,
omega R2C.
okay.
If I substitute omega equal to 0, it is minus 3 tan inverse 0. Tan inverse 0 is 0. So minus 3 into 0, it is 0 degrees only.
Okay, so you are saying in that way. Okay, if we come from your perspective also, so this becomes minus tan inverse of,
If they took 180 degrees, then it is 540, madam. Why they are
huh,
taking 180 degrees?
uh, tan inverse 0 will give you 0. Tan inverse infinity will give you 90.
90 degrees.
So that will come out to be 270 degrees, right?
Hmm.
Which is sort of less than 360. So is this the only, so minus 3 tan inverse is the only phase that you are observing?
Madam, if they are saying oscillate means the phase shift should be 0 or 360, right?
Yes.
No, we are getting minus 270 only, na?
Maximum minus 270, right?
Mm-hmm.
Hmm.
Either it should be 0 or 360.
Yes.
Then in one case, how it will oscillate, in other case, how it will won't oscillate.
Yeah, your argument is right. Because see, if I say my phase is this much only, then what is the maximum ranges that I can shift? So omega RC can maximum go to infinity. If omega RC maximum goes to infinity, then the phase that I get maximum is minus 270. And either I can have omega RC as 0, which is the minimum possible value. I cannot go below that. At that time, my phase will be 0 degrees. So my phase will be somewhere between 0 to minus 270 degrees. Right? So but okay, so the total phase, so this minus 3 tan inverse omega RC, is this the total phase or the phase of feedback? That also depends, right? This minus 3 tan inverse omega RC, is
Yeah,
this
if you are taking it as a feedback, op
huh,
amps are operating in inverting configuration.
okay,
All three op amps, let us assume each will provide 180 degrees phase shift.
right?
Then three, 180, 180, 180.
Hmm. So is it minus plus? Then again minus plus. Then minus plus. Is this the configuration that we are going for?
Yes, madam.
This is the same configuration, right? Everywhere.
It is acting as an integrator. So we are saying that 90, 90, 90, 270, right, madam? In integrator. If I'll provide sine, it will provide cosine. So the phase shift will be 90 degrees, right?
But it also depends on what frequency you are using.
Hmm.
So because it is a low pass filter in lower frequencies, and in
Hmm.
higher frequencies it will act as an integrator. So it also depends on what frequencies
Hmm.
you are looking into.
Yeah.
Yeah. So that's what we said. No, if omega RC, the maximum the phase that you can get for tan inverse omega RC is 90 degrees. That is when omega is very high, and for lower omegas it will be lesser.
My question is only if I change R1, R2 values,
Huh.
or the phase shift will change. Suppose in earlier case R is 1 kilo ohm, in this case R2 is also 1 kilo ohm.
Hmm.
If I change R1 value, then gain will be disturbed, not frequency.
Okay, let's see. R1, R2, C, right? So here, if I write my transfer function, V out upon V in, this is um,
R2 by R1 divided by 1 plus
just wait a second, R1 into 1 upon CS by R1 plus 1 by CS upon R2, correct? This is right?
yes.
So then,
It is like minus R1 by R2 divided by
CS,
yes R1C plus 1.
R2, R1 CS plus 1 by CS. So this 2 will be cancelled. So this is what we will get, right? Minus
Yes.
R1 by R2
Hmm.
into 1 by R1
Hmm.
CS plus
R1
1.
by R2 is the gain and that will be the pole.
Yes, minus V out by V. So here if I, let's say this is my G. So if I write
Yeah,
the gain
angle will be
phase,
minus tan inverse imaginary part by real part, right?
no, minus 180 also, right? Minus
Mm-hmm.
is tan inverse.
Mm.
Okay, this is R1 CS.
Yes.
Now since there is,
If omega is 0, minus 180 degrees. If omega is infinite, then minus 270.
yes,
minus 270 minus of minus 180, it won't be 0 degrees or 360. They wrote that only in the solution manual.
So, but in so if this is the phase of my one this thing,
Yeah,
right?
yeah. If it is 3, we have to multiply 3 with the 3.
Yes. So if it is 3, I have to multiply whole with 3, correct?
Yes, yes, yes. Minus 5, minus 540
Minus 540
minus
minus
3 tan
tan
inverse.
inverse
Hmm.
R1CS.
Hmm.
Okay. So considering that R1C is like equal in all the three uh,
Hmm.
things, so this can go from 0 to 90, right? So based on that, what is the angle minima that we will get is minus 540.
Hmm.
What is the angle maxima that we will get? Maximum we will get is uh,
540 minus
560 plus
270, which is 270
270.
minus 270.
So 810, right? Minus 810,
Hmm. Yeah.
correct?
Hmm.
So this is the minimum phase that you can obtain. This is the maximum phase that you can
Hmm.
obtain, right?
Yes. Hmm.
Now, if this is the minimum phase, this is the maximum phase, there would come some phase in between, right? For some value of omega,
Hmm.
where you would get the angle to be of 720 degrees.
Hmm.
You will get it.
Yes.
And you know that when you have this angle of 720 degrees, it is multiple of 360, right? So there definitely your circuit will oscillate, correct? Now see here, 0 and 90 degrees that you got, what were you changing? You were
I got your
changing
answer,
the
madam.
omega.
I got your answer. My
Yes,
question is, if
yes.
R1, R2 values are different, they are
Huh.
saying oscillating. If they are equal, they are saying does not oscillate. That is my question. I understand this analysis.
Okay. So if it is same, then what is the issue?
Hmm. Gain will be 1. That's it, madam. We'll get same. There is no change in the phase shift. If
Yes,
I
because
substitute R1, R1 by R2 get cancels.
yes, 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 that is true. R1 and R2 will get cancelled.
Hmm.
Then, okay, so this we are coming from phase point of view, right?
Yes, yes,
Maybe
phase.
while calculating the magnitude, there might be some concern because of which the issue is arising. Is it
Madam,
possible?
magnitude means output or I mean gain may be 1 or 2. It depends. If you go with RC phase shift oscillator, then it will be minimum 29. And if
Yes.
I'll go with Bean Bridge, it will be 2 minimum.
Mod of gain, if I want to calculate the gain, how will my gain look like? It is R square C square omega square plus 1, right? This is the gain for, let's say, my forward path. Now in my feedback path, what I need is beta G into beta should give me 1. So there are feedback. So there are 3 op amps. Let's say one I consider for forward path, and this if I consider for beta, and all are same. So if all are same,
No, we cannot
yes,
consider right, madam. Why? Because the last op amp they are taking the output. They are saying in this case
huh?
it is oscillating means we have to take the output at the last op amp.
Here you will take output.
Yeah.
So, but there should be a feedback, no?
Yeah, in feedback directly they are connecting. So I think unity feedback one as per our control system terminology. So three op amps are there in the forward path and feedback path. Single line is there. It will be unity feedback.
So you are considering 3 op amps in forward path and a
Hmm.
single unity in feedback path.
Hmm.
So my question is, using 3 op amps in forward path and single unity in feedback. So will
Madam,
it will
if you
it
see
get
the phase shift oscillator and green bits, only one op amp we are consider, and in feedback we kept only R and C components.
yes,
We doesn't place op amps, right?
yes, but
Then
we
how
can
to make?
place op amps there. We can place op amps in between our C factors just to get the buffering effect. So there
Yeah,
the
voltage follower we can, but this is not voltage follower, right? If you want to use it as a voltage follower, then R to R1 value should be same.
Mm, no, but that is where my question is. Say feedback, you are saying you are giving a unity feedback.
Hmm.
So at the end, for satisfaction of Barkhausen criteria, your G into beta should come out to be 1. Now
Hmm.
we are saying that mod G for one op amp for R equal to R is 1 upon root under R square C square omega square plus 1, right?
Yes, correct.
And since like op amps are connected back to back, so the gains will be simply multiplied, right? Because you don't see a loading effect. So this becomes R square C square omega square plus 1 ka whole cube, right?
Hmm. Yes.
There is no doubt in this,
Hmm.
है ना?
Hmm.
So which brings us to the point that, okay, so if this is root and we are saying that beta is 1, right? Now this is G G total. What we want is G total into beta should give me 1. Is there a possibility that these two multiplied will give us a value of 1?
At omega equal to 0, we'll get.
At omega equal to 0, no.
Hmm.
But the point is at omega equal to 0, omega equal to 0 means it is DC.
Yes.
So there is no frequency at all.
Yes. So at any frequency, it won't satisfy that condition.
Yes, because omega equal to 0 means DC. DC means
Yes.
no oscillation is already not oscillating.
Hmm.
है ना?
Hmm.
If it would have even gave me 1 hertz, then also I would say it is oscillating. But omega equal to 0 means it is already DC.
Yes.
So if it is DC, this condition would never satisfy. So that is the point. For satisfying Barkhausen criteria, actually you need to satisfy both the conditions. A into beta equal to 1 as well as your phase should come out to be total
Then
phase.
how will one op amp we have to take in forward path and two op amps in feedback path, or two op amps in forward path and one op amp in feedback path?
No, but it also depends on where you are taking your
Output.
output from. Yes.
Hmm. They did
That
not mention
also
where we are taking the output.
that also depends. But see, anyways, you want to divide it, right? Here you divided it this way. If
Hmm.
otherwise, say, if you keep like two op amps in forward and one op amp in feedback, then also this condition will never satisfy.
Yes.
है ना?
Hmm.
So that is the thing. So this condition is never being satisfied, no matter which op amp you consider in forward path and which you consider in feedback path. Because if I take my output from here, then the remaining this would be my feedback path.
Hmm.
Because the idea of feedback is that, right, from where you are feeding your output to input.
Yes.
So wherever you are feeding your output to input, that path is feedback.
Hmm.
So the remaining will come into feed forward. That is the idea. But more or less, the complete circuit is so in this Barkhausen criteria, you actually analyze the complete circuit. No matter where you take the chunks from, it comes out to be a total analysis, right? Because you analyze feed forward as well as feedback paths together.
Yeah, I understand. In one case it is oscillating. In other case, why it doesn't oscillate? If
Yeah, because see, here I
we change
analyze.
R1 R2.
Yes. We analyzed both of them, right? We
Yes.
analyzed in case of R1 and R2.
Hmm.
By using the phase analysis, we analyzed and we found out, okay, there would be only one
Hmm.
frequency where we can get this Barkhausen criteria satisfied. right? But when I substituted R1 and R2 as R, at that time when I tried to go for my this analysis of gain, the Barkhausen criteria didn't satisfy. Now, if I try to analyze it for, say, my what this thing phase. So phase के लिए what will happen? It will be minus 180, then minus tan inverse RC omega. Okay, but here, right. So here for phase again we will need to go for 3 times, no? So for phase, according to phase, it is satisfied. But for gain, it is not satisfied. But since there we have R1 and R2 different, then what is happening if R1 and R2 are different? At that time, they will also take part in your gain calculations. So, if they will take part in gain calculation, I can somehow manage, right? If I have my G as minus R2 by R1, R1CS plus 1. If this was my transfer function, okay, and I'm writing its gain, so how it would be R2 by R1 root under R1 square C square S square plus 1, correct? This is my gain, and now I am saying that it is back to back 3 gains, so this will become, this is basically cubed. So since gains are multiplied, so this is R2 cube by R1 cube and root under R1 square C square S square plus 1 ka cube. So in this case, is there a possibility that I can get 1? Can I get 1 in this case? I can get a 1, right? Hello? Hello? Am I audible? Oh, okay. So I guess the student has left. So in this particular case, when R1 and R2 are different, since R2 is a different value, R1 is a different value, there is a possibility for some combination we can get this mod G3 like G cube as 1. If R2's value is selected in such a way and omega is also selected in such a way that this satisfies. So there is still a possibility that we can get oscillations for different R1 and R2. But in case of same R1 and R2 equal to R, there is no way possible that we can get a gain perspective. From the gains perspective, we will never be able to satisfy the Barkhausen criteria. So that's why this circuit will never oscillate. Yeah, that is the idea. Okay. So I hope this is clear. But if you have any concerns, you can directly raise in the forum, because I guess forum is an easier and interactive way in which you can connect with the team efficiently. So yeah, that's all for today. If you have any other doubts, you can feel free to ask. Else, we'll meet on Monday with the new set of concepts and problems. So that's all from my side. Thank you. Have a wonderful evening ahead. See you all. Bye.